SwayamPrabha. Digital India. Educated India.
So, we are going to discuss about age hardening systems today and trying to explain you how in aluminum copper alloys the phase transformations of precipitation formation and its growth can control its mechanical and physical properties. Basically, we have discussed so far that aluminum copper, especially the aluminum rich copper alloys, undergo precipitation hardenable phase transformation, and here in this slide I am showing you a part of the phase diagram of aluminum copper. As you see, the phase diagram which involves alpha phase and the liquid plus alpha phase is shown, and on the top of which there are a few dotted lines, and these dotted lines indicate the formation of the transient phases during aging treatment of aluminum copper alloys. The most important alloy is aluminum 4 weight % copper, which is known as duralumin, and as you see here, the typical phase transformation, typical heat treatment cycle which leads to precipitation hardening is kind of like this. If I take a aluminum 4 weight % copper alloy, first thing we do is we heat this alloy to the single phase region, and because of this treatment which is known as annealing treatment, all the precipitates which are present in the alloy dissolve in the alpha phase, and then we form a single phase homogeneous alpha, and this is followed by quenching to room temperature. Okay, just quenching means just take the alloy at a high temperature and put it into water directly. So, therefore, there will be a change in the there will be a rapid change of temperatures because of this treatment, and which will allow all the copper atoms present in the aluminum retained in the microstructure. And the next one, which involves aging, is basically nothing but heating this alloy to a temperature between 150 to 200 degrees Celsius temperature. So, 150 to 200 Celsius temperature, okay. This is 100 and 200. So, something around 130 to 190 degrees Celsius in the temperature range, these alloys which are quenched are given treatment for different time duration, and because of that precipitates form, and we have seen that precipitation formation is basically happens in a stage, in a manner which is some sort given by these. First the GP zones forms, is followed by theta double prime and theta prime, and then finally the equilibrium precipitate theta, which has a composition of Cu2Al forms, that we have seen. And I have told you that this can be explained using free energy composition diagram such like this. Let us not go back into that. It helps you to explain different equilibrium compositions between these transient phases, GP zones to theta double prime and theta prime with the alpha, and this can be easily then described. To give an perspective that this all you know that GP zone is nothing but a few layers of copper atoms sitting on these 100 planes of aluminum, alpha aluminum lattice, and then theta double prime and theta prime is basically some sort of coherent structure along the different interfaces as described here. Theta double prime has a coherency along all interfaces, therefore, it retains low energy interfaces with the matrix theta double prime. Theta prime actually has coherent or semi-coherent along 001 planes, but non-coherent on 100 or 010 planes. And on the other hand, theta, which is equilibrium precipitate, is completely incoherent structure. So, therefore, the tangent phases actually help us produce different kinds of interfaces between these phases and the matrix. This is what I told you also. And some of the microstructures which is shown you again, show me because this helps you to understand. GP zones as basically is nothing but extra 1 or 2 layers of copper atoms on the aluminum mono planes. So therefore they lead to a strain matrix which is shown here. Similarly, theta double prime is also coherent along all interfaces. Only thing it can lead to in the microstructure is such a kind of a coherency strain, which we have discussed in our previous lectures. So this will lead to a certain kind of a strain matrix, and this is what's seen here. These are the theta double prime precipitates. Theta prime precipitate which looks like a much bigger, they are again elongated, long, and theta is basically a very well defined precipitates with no coherency along any of these interfaces. So that is what is the truth. And obviously nucleation of these phases happens along the Gantt boundaries or the dislocations, and this can be used to alter the microstructures. As you see here, the Gantt boundary is present in which theta is precipitated. Similarly, theta prime as precipitated along a certain Gantt boundary. So it is possible to precipitate these nucleate these precipitates along the defects in the matrix. Now let us first discuss actually what happens. That was recapitulation. What actually what happens when you heat treat these alloys during aging treatments. I am showing you the plots which are taken from this paper by Silcock long back. It's in 1954, and this actually is very this tells you actually what happens in during aging treatments. Let us look at the top part of that. What is plotted here is the Ficker's hardness versus aging time in terms of days for different concentrations of these alloys. Okay, and the aging treatment, similarly the bottom figure is same thing, only difference is that the aging has been done at higher temperatures, at about 190 degrees Celsius temperature, sorry. And so let us first look at the top curve. As you see here, if you look at 2-8% copper alloy, which is a very lean copper, aluminum copper alloy, the aging treatment at a lower temperature, 130 degrees Celsius temperatures, gives you a, takes a lot of time to start the precipitation. Basically it takes about 10 days to start the precipitation. Basically that is the time in which GP zones forms. Then slowly hardness increases, and it takes about 200 days to get a optimum hardness. So that is the problem using a low aging temperatures. If you say low aging temperatures, kinetics of formation of these precipitates is very low. It's little bit improves if you increase the concentration of copper, because copper is what is leading to the formation of these precipitates, starting from GP zones to theta double prime and theta prime. But you see it takes quite a lot of time, about 50 days to reach a peak hardness. The peak hardness means the hardness actually starts with a very low value initially, then increases and reaches a maximum, then again decreases. This is a typical hardness curve or aging curves which I have already discussed in the last lecture. So the peak hardness means the temperature or time at which the hardness is achieving the maximum value. So as you see here, if its aging is done at about 130 degrees Celsius temperature, the time required to achieve peak hardness for alloys with 3 to 4.5% copper alloy does not change, it remains same. On the other hand, if we age at 990 degrees Celsius temperatures, which is about 60 degrees higher than this, the peak hardness time required to achieve the peak hardness is very low. It can be obtained even less than 1 day of heat treatment. It is about something like 6 to 7 hours is enough. Not only that, even for the very lean copper alloys like 2-8% copper alloys, it requires about 7 to 8 days to achieve the peak hardness level. So that means what? The aging temperature has a profound role in defining or in leading to the formation of these precipitates, and which can actually lead to very interesting aspects in the actual production. Because when you are preparing these alloys for these, or actually when you are doing the heat treatment of these alloys for different components, important aspect is to reduce the time. But if you want to reduce the time quite a bit by increasing temperature very high, it leads to coarsening of the precipitates very rapidly. That is also a problem. So therefore the optimum temperatures of heat treatment for the most of these alloys during aging is something around 150 to 170 degrees Celsius temperatures. So 190 is actually a little on the higher side, 130 is on the lower side. So these particular view graphs tells you that these heat treatment or aging treatment must be done with the optimum selection of temperature. And remember these points which are shown here, the points are basically for theta prime because this tells you what kind of precipitates this form. Surprisingly, if you look at the lean alloys, okay, just after GP zone, it directly goes into theta prime, as you see here. But on the other hand, for the little richer alloys with 4 and more than 4% copper alloys, or 3 actually, 3 and more than 3% copper alloys, the sequence is all just like what we see in the real microstructural length scale, that is GP zone followed by theta double prime and theta. And obviously at a very high temperature or very high time, theta will precipitate. That is what is not shown here, but that is not actually desirable because theta has incoherent microstructure interfaces with the alpha. So therefore, the hardness decreases further. So why such a curve? Why is this such a kind of behavior you observe? First of all, GP zones are basically what? They are actually copper layers sitting on the aluminum planes. I have been telling you again and again. So these copper layers actually start blocking the dislocation motion. But because there are only few layers of copper atoms, the hardening is not very high. Hardening is basically coming from the coherence strain which is generated in the matrix. So therefore, the hardness increase because of the GP zone formation is not very high. But the moment the theta prime or theta double prime actually start forming, the hardness increases very rapidly. The reason is very simple. Theta double prime, as you see here in the previous plots, theta double prime is this structure. It has a tetragonal structure built in automatically with A and B is same 4.04 Armstrong, but C is about 7.68 Armstrong. Okay. And it consists of alternate 2 layers of copper on the both sides of the 001 planes of aluminum. Inside you have aluminum layers. You see here that this round, these open circles are basically aluminum and the closed one is copper. So basically it develops 2 layers of copper on the both sides of the aluminum. And these layers of copper actually leads to distortion of this lattice or rather increase of the C axis of the lattice and gives you a theta double prime tetragonal lattice. So, but very interestingly, although this forms a kind of structure, all the interfaces, whether it is 001, 100 or 010, that means all the faces of this tetragonal unit cell remains coherent with the aluminum lattice. Aluminum is shown here, and this coherency is basically gives the increase of hardness more, because as the dislocation moves from the alpha to the precipitate theta double prime, there is this strain or this basically the between the precipitate and the matrix there is a stress developed because of this coherency strain, and this stress actually block the dislocations to move inside these precipitates. Because as you know, if the precipitate is present in the matrix like this and a dislocation needs to move like that, a dislocation is present somewhere there and it has to pass through it, and if the matrix and the precipitate has a coherent microstructure, only way dislocation can pass through is by cutting it through. That means it has to create 2 new interfaces. If it has to move here, this precipitate which is shown here will be cut into 2 pieces, okay, and that is what happens, okay. And because of these cutting methods, precipitate size is very small obviously for the theta double prime. And so because of these 2 new interfaces generated, so work done is pretty high, and that is why the dislocation motion is hindered. But on the other hand, as the theta prime forms or phase transformation at the higher time or maybe at higher temperatures, whichever is true, theta prime is going to be forming, and theta prime has also tetragonal lattice structure. But difference is that theta prime atomic elements is different. As you see here, the 2 layers 001, okay, on the top and the bottom actually they consist of aluminum atoms. On the other hand, the central layer is also aluminum atoms, and from these copper atoms present at the different corners or the faces of these tetragonal lattice. So because of that, this phase loses its coherency along 100 or 001 planes. That means coherency along these 100 planes are these ones, these facets, these are the 100, and 001 planes are these ones. So they lose the coherency. Only coherency maintained is on the aluminum positions, on the top and bottom planes. So because of that, now dislocation has 2 choices. Either it can cut through this precipitate or it can form a loop, around it when the dislocation move. It can form a loop around it when it passes through. Obviously, dislocation will come like this and then slowly bend it, and then once it bends it can basically form a loop like this. Okay. So, finally, it will leave behind, this is the precipitates. Okay, let me tell you. So, this is let us first remove this part. Okay. So, this is the precipitate and it comes close to the precipitate, then it bends and then finally it loops behind a loop and then it moves ahead. So, because of that, because it creates a loop around the dislocation, this is known as Orwan's mechanism. Because of that, the new dislocation which is coming again will be subjected to a stress field generated by the loop. So, more number of dislocation passes to more loops will be forming around these precipitates, and the stress field generated will be higher, and that gives this strength. But remember, this depends on the distance between these precipitates present. If the precipitates has to be in a particular separation, otherwise this kind of bowing of dislocation leading to formation of a loop will not happen. So, that is why the precipitate size must be a little bigger as compared to theta double prime. Theta on the other hand is basically a completely incoherent structure. So, only way dislocation can pass through is making the loops around it, and they will be obviously bigger in size because the growth will happen at a higher temperature time. So, because of that the material loses strength slowly, and that is why the hardness slowly drops off. So, that is the main reason why you see such a kind of aging curves in the microstructure or in the real heat treatment. So, therefore, if I want to create a good material which will be applicable for the various potential applications, so we need to have combinations of good hardness and the ductility, and that is only possible when you have on this side of the curve, okay, on the rising side of the curve. Okay, that is what I am showing you here in all the cases. So, if the heat treatment is done in such way that the temperature and time is selected properly, then we can be hardness can be made on the increasing side of these hardness plots, and then we can achieve a good combination of the strength and ductility. That is what is actually done. So, the selection of these heat treatment temperature and time has to be judiciously done, otherwise alloys will not be applicable in real applications. That is very important aspect which you must remember. There are other things which you should also remember. You have to understand that these precipitates which are forming, they are forming basically or nucleating on the grain boundaries or on the internal dislocations present near the grain boundaries as well as within the grains. So, we can actually improve the aging efficiency or the ability of the alloy to age very nicely by adopting two different approaches. One, which is very routinely done, is that after solution aging treatment and followed by quenching, the alloy can be given a deformation, plastic deformation, which is simply rolling it or giving a forging treatment. But doing that, we create large number of dislocations or defect structure in the alloy in the sample, and then if this is followed by aging treatment, that means this deformation is given prior to the aging treatment. Deformation will lead to dislocation and defect structure, and then the aging defects will allow the nucleation of these precipitates very easily. So, therefore, one of the ways to achieve faster aging and better distribution of the precipitates in the microstructure is to give a prior plastic deformation prior to the aging treatment. Other way is to use what is known as double aging treatment. Double aging treatment means we can actually have aging treatment done at a lower temperature, something like 120 degrees Celsius here, and this will only lead to formation of GP zones. Large number of DP zones will form because other precipitates will not form at the temperature. GP zones will be preferentially forming across the whole microstructure or across the whole sample. Then this sample can be again taken to higher temperature, like something 170 to 175 degrees Celsius temperature, and kept there for some time. As the GP zones has homogeneously formed in the microstructure because of the lower aging temperatures in the first stage, this will allow the formation of the precipitation of the precipitates like theta double prime and theta easily on the GP zones. So, by using either a plastic deformation prior to the aging treatment or by using a double stage aging treatment, we can actually improve the mechanical properties of these alloys extensively. and these are routinely done in the actual practices. Actually all the alloys which are used for the aeroplane body is normally heat treated or aging treatment is done after the plastic deformation, just to increase the nucleation density of these precipitates in the microstructure. Okay, another important aspect which I already discussed, let me tell you again, using these kinetics of the heat treatment or aging treatment, one can actually generate something like a time temperature transformation curves. Although it is not truly TTT curve, but it can be. So here, as you see here, this is the phase diagram which is shown alpha and theta, and these are these dotted lines which are corresponding to the different transient precipitates, GP zone, theta double prime and theta prime. Now we can have something like a nucleation and growth kinetics built into that, and these curves are obtained like that. Obviously this looks like a Johnson-Mell equation which is available for the steels. Why? Because if you look at any transformations, the transformation rate depends on, if I plot time as temperature versus time, transformation will be maximum at some intermediate temperatures, at higher temperature it will be lower, and lower temperature it will be lower. This is mainly because at high temperatures the diving force available is low. So therefore nucleation and growth rates are low. But lower temperatures nucleation diving force will be higher, but because diffusion is slow, so therefore growth will be slow in a precipitation hardenable or diffusional transformation by the way. So that is why you always see a C-shaped curve. So at the intermediate temperature somewhere between that, both the optimum value of nucleation rate and growth rate can be achieved, because diffusion as well as the diving force both has to be optimally chosen. And that is why all these curves have a C-shaped nature. And GP zones, because it forms at a lower temperature, so therefore they will be starting at a lower time scale, a lower temperature both, followed by theta double prime, theta and prime and theta. So these curves allows you to select the heat treatment cycles, right. You can clearly see this is the time log, this is the temperature. So if I simply do a double heat treatment, first I can simply allow these things to happen like that. So therefore large number of GP zones will form in the microstructure, then I can heat it up little higher temperature and keep it there long time. So it will allow me to form large number of theta double prime on the existing GP zones, and that is why it can be done. In fact, in many of these actual practices, sometimes people give them a 3-stage heat treatment, heat it up and keep it there also. So you can actually have combinations of GP zones, theta double prime and theta prime forming in the microstructure and give you the optimum value of the hardness. So such a kind of TTT curves or transformation temperature curves can allow you to basically select your heat treatment cycles very nicely. Okay, so that is the important part. And another important thing which I should discuss is that, as you know, this is important because of the heat treatment cycle which you do. Remember that the first thing we do in the heat treatment cycle is solutionizing at a high temperature, something like about 500 to 550 degrees Celsius temperature for the aluminum copper alloys. Because of the solutionizing temperature, all these precipitates theta prime gets dissolved into the alpha matrix, and at a high temperature obviously this is done. So therefore there will be large number of vacancies created at high temperature. As you know, the equivalent number of vacancy depends on the temperature in a particular material. So high temperature there will be large number of vacancies created, and they will be remain as a equilibrium defects. Now as a part of the heat treatment, this high temperature solutionized treatment is always followed by quenching at room temperature. So as we quench at room temperature, all the precipitate, all these vacancies which are formed will be quenched in the microstructures. Now these vacancies which are quenched in from the high temperature low temperature has a preferential role or very important role to play, because these vacancies can then coalesce and form vacancy loop, and they can also form dislocations. They can lead to cross slip also of dislocations because of the availability of these things. But most important thing they can allow it to happen is the diffusion of the copper atoms, because diffusion normally happens in the substitutional solid solutions by vacancy movement. So the vacancies are actually present in large number during aging treatments. This allows us to diffusion to have faster. That is one important aspect. As I told you, diffusion has a sink. Dislocation will act as a sink for the diffusions, because for these vacancies will form a loop, and this can be again lead to formation of dislocations. There is another very important sink in the microstructure for these deficiencies, that is the gain boundaries. Gain boundaries are basically haphazard structures if you look at it, and because of that these deficiencies can slowly move into the gain boundaries and get sunk by the gain boundaries. So therefore, if I plot the distribution of the fraction of the vacancies as a function of distance between the two grains, as you see here at the gain boundaries, the vacancy concentration, equilibrium vacancy concentration is basically very low. So therefore, these vacancies which will be present at the gain boundaries will not allow the precipitates to form, because for the precipitates to form you need certain minimum amount of copper atoms, because GP zones actually is nothing but the copper layers present on the alpha aluminum FCC lattice. So because of that the G zones in the gain boundaries will be precipitation free, and these zones are called precipitation free zones or PFZ in the literature. This is widely seen. Obviously quenching rate also has a role. If you quench very fast, as you see here, if you quench very fast, you retain certain amount of vacancies inside the grain, but at the gain boundaries there is a rapid drop of the vacancy concentration. That is because gain boundary acts as a sink for the vacancies. Vacancies will go and get lost in the gain boundaries. So there will be reduction of the vacancies concentration in the gain boundaries, and because of that obviously the copper atoms cannot form these GP zones and precipitation is not possible. This is widely observed in the microstructure, like this one you see here. These are the three gain boundaries or three gains meeting at a point. So near the gain boundary there is a precipitation free zone present, which is widely observed in the aluminum zinc magnesium copper alloy, and these precipitates here actually also theta GP zone and theta double prime. Okay, so in the last at the end of this last portion of the part of precipitation hardening, let me just tell you, aluminum copper is not only the one alloys which undergoes precipitation hardening, but there are many others. One of the important one is silver aluminum, which I mentioned in the last class. Silver aluminum also forms two phases, as you see here. What are the phases it forms? This is alpha phase, this is aluminum bridge. Silver concentration is something like about maximum is about 80% at the eutectic temperatures, and then you have a equilibrium between gamma and the alpha. Gamma is actually hexagonal structure here, and because of that gamma has hexagonal structure, and because of that these alloys also undergoes precipitation hardening. And the way things happen is this, again let me not discuss the whole thing. Alpha 0, which is supersaturated solutions, it first forms alpha 1 plus GP zone, then it becomes alpha 2 plus theta gamma prime, and then alpha 3 plus gamma. Remember, gamma prime and gamma both has hexagonal structure. On the other hand, alpha has a FCC structure. So therefore, the only orientation relationship which is possible, which can lead to coherency between these precipitates, okay, gamma prime or gamma, basically gamma prime, is such a kind of things that 001 plane of gamma prime must be parallel with 111 plane of alpha. Similarly, 1 toward 0 direction of gamma prime must be parallel with 110 direction of alpha. So that allows to have the coherency between the precipitates and the matrix phase, and it is seen to be specifically observed. Only problem is that because of the silver, which is expensive material, these alloys are not used so much. But as you see here, these alloys can be used actually little higher temperature than the aluminum copper alloys, because the solvers which is shown here can actually go up to 550 degrees Celsius temperature. So the treatments will remain same. Again, you take any alloy, heat it up to the solver's temperature, above the solver's temperature, then followed by quenching, and then one can do heat treatment at different temperature, either here or little higher depends on wherever. So that is this routine way of doing the things. Here again basically the precipitates, the final gamma precipitates is Ag2Al, and they are actually plate separate. There looks like a plate like aluminum Al2Cu, and the behavior is almost similar. Okay, so let me stop here for the this part of this portion of this lecture. In that, so therefore, precipitation hardening is basically an important class of alloys, and these phase transformations are to be nicely known to all of us, because they becomes a very important class of alloys. And there are many such. I have only taken the example of aluminum copper to explain you the different aspects of the precipitation hardening, and I have given you at the end some example from aluminum silver alloys. So in the next lecture we are going to start with another diffusional transformation that is known as Utrecht transformation.